Thank you.
So today we have I think, rather simple presentation for you, but we hope it could end up being something quite useful. And what we've done together with Marian is to develop a very pragmatic approach to regularization of failure simulation under different states of stress. "80% of the problems you're going to have in your life are battery related." Not saying we should get rid of batteries. I didn't say that. Where was I? So failure in metals will always be the result of some damage process. But prior to that failure, we will usually see a process of localization of plastic deformation. That means we lose the homogeneous state of deformation. We localize plastic deformation in a small area. And that localization, when we simulate it, will inevitably be mesh dependent, which is why we need regularization. Now, we usually distinguish between brittle and ductile failure. Ductile failure means that you localize prior to failure, and that means you will have to regularize. Brittle failure, in my terminology, is that there is no localization prior to failure. So you break before your neck, and then there is no need for regularization. Now, the important thing that we're going to try to convey today is that brittle and ductile are not material properties. Any material is brittle and ductile depending on the state of stress to which it is subjected, and it will have to be treated accordingly. So what happens when we localize? Well, when we localize, there is inevitably what I call an instability. You see a negative slope in the force displacement curve. So you get a negative stiffness. I call that an instability, not everybody does. So there's two different kinds, right? Because the force is equal to the true stress times the cross-section. You can either have an increasing true stress with displacement and a decreasing cross-section. That's what we call a structural instability. Or you can have the reverse. You can have an increasing or a constant cross-section with a decreasing true stress, which is a softening, and that would be a material instability. An example of the first is necking. An example of the second is a shear band. Now, not everybody, as I said before, calls it instability. If we look at necking, and in particular diffuse necking in a metal, people will usually identify that with a loss of uniqueness. And clearly, if you look at the force displacement curve for a tensile test on a piece of steel, the necking starts in the maximum. And once you are beyond necking for a given force, you match two displacements. So you lose the uniqueness of your solution. And at the very minimum, when you do an implicit solution, that may cause problems. Now, the term instability will often be reserved for material instabilities, and that could be adiabatic shear bands, it could be PLC effects, it could be material softening, it could be many things. I don't distinguish. Loss of uniqueness is bad enough. The point is, you become mesh dependent. So it's very important to know when it starts. Well, if you have a very nasty, difficult question, you can always ask Sir Rodney Hill, or at least you could, as long as he was alive. And if you go back to the literature, in 1956, he published a paper which actually gives a mathematical criterion for the onset of localization of plastic strain, which he identified with the loss of uniqueness of the mechanical problem. But if you look at the formulas there's an integral. And that integral goes over the entire domain. So it's a global criterion that depends on the material law, on the boundary conditions, and on the geometry of your structure. It's not something that you can evaluate at the level of the integration point. So for implementation in a code, it's maybe not very practical. Now, note that he published that paper in 1956. That's the year I was born. That's why I didn't read it. I was too young. Let's focus on necking a little bit. What is going on in a piece of steel that we subject to a tensile test? Well, you can actually distinguish four phases. Initially, you have homogeneous deformation. Then you have what we call diffuse necking, which is essentially a reduction in width of the sample. And then you have localized necking, which is what metal forming people are interested in. So you get extreme thinning in a narrow, skewed band through the sample, and that will then ultimately lead to fracture. Now, the criterion for the onset of diffuse necking has been known since 1885. It was Considère who identified it with the maximum of the force displacement curve, or to put it differently, the maximum of the engineering stress, engineering strain curve. Again, Rodney Hill identified the start of localized necking as the point where the second principal strain stops growing as the first principal strain is further increased. And at that point, the only thing that your material can do is thin, and obviously the process accelerates very rapidly from there on. Now we can look at that in terms of yield curves. The condition that you have a maximum in the force displacement curve is the same as saying that the tangent modulus is equal to the true stress. If we then neglect the elastic strains, we can say for metals with a good approximation that diffuse necking starts when the hardening modulus, the derivative of the yield stress with respect to the equivalent plastic strain, becomes equal to the yield strength. And if you then throw a very, very simple equation at the yield curve, like the Ludwig equation, yield stress is equal to K equivalent plastic strain to the power of N, and you do two lines of algebra, you find that the diffuse necking starts for an equivalent plastic strain equal to N, N being the hardening exponent. Now, with an additional two more lines of algebra, you find that local necking starts at 2N. So it's quite far away. A little bit more of a closer look at that, because it's all important in the end in terms of states of stress. As long as we have uniform deformation, we have a uniaxial state of stress, and we could actually easily simulate a tensile test with a single element. But then when we start necking, our state of stress changes. It becomes two-dimensional. And at that point, we need a shell mesh to adequately model what is going on. Finally, when we have local necking, we not only have width gradients in the sample, which cause a transversal stress, but we also have thickness gradients, which cause the stress in the thickness direction. So at that point, the problem becomes three-dimensional, and we theoretically need solids to model it. Well, that's all very good. We don't do that in practice. We use shells. But that, of course, contributes to the problem of mesh dependency, because once we start to see a local neck, we not only see mesh dependency, but we enhance the localization because there is a component of the resistance of material that through the thickness stress that is missing in our model. Now, that's not a cause of the issue. It just makes it worse. So I now come to the mesh dependence. I apologize for the simplicity of this example, but I have to make sure that I get rid of the last bit of doubt about the fact that there is mesh dependency once you reach diffuse stacking. Imagine the extremely simplified case of a rigid, perfectly plastic material. So you have a Young's modulus that goes to infinity, and you have a constant yield stress. When do we start necking here? For which plastic strain do we start necking? Well, it's immediate. You start at 0 because your hardening modulus, which is 0, is smaller than your Young's modulus, than your yield strength, sorry. And that happens immediately. So the moment you load, you're going to localize. And this case is actually so extreme that you can try it out in OpenRadioss if you don't believe me. But all plastic strain will localize in a single element. Now let's assume that I can put my hands on some of that material and I do a tensile test on it. And I have a sample with an initial length L0, and I have a final length L at which that sample fractures. And now let's assume that I'm a professor at Chalmers, which I'm not, but we will assume that for just a moment. And I asked one of my students, work out the strain to failure, knowing the final length of the sample when it fails. And the first student I ask is not the most studious. He models my sample with 2 elements. All the strain localizes in one of the 2. He looks at the maximum strain, which is in this element, and that strain is logarithm of the final length of that element, which is the final length of the sample minus half the initial length of the sample, the other element, divided by the initial length of the element, which is the initial length of the sample, divided by 2. And he says, here is your answer. So I'm not convinced. I ask a second student. He likes work more. He puts 4 elements. And he comes with a completely different answer. Because once again, all the plastic strain, and there is no elastic strain, concentrates in a single element. So the strain in that element is final length of the sample minus what is left in the other 2, 3/4 of the initial length, divided by the initial length of that critical element, which is the initial length of the sample, divided by 4. Completely different number. In general, if I have n elements over the length, I get that formula for the strain in the right upper corner. And there is no way that you can eliminate n from that formula. But what you can do is you can reformulate the whole thing. And you can say, well, I have a global strain, which is the logarithm of the final length of the sample over the initial length of the sample, or the logarithm of the displacement over the initial length of the sample plus 1. And you have a local failure strain for which we have the formula in the right upper corner. Now I can get rid of n by replacing it by the element characteristic length, which would be the length of the sample divided by n, the number of elements that I use for the discretization. And then you see that the local strain is the logarithm of displacement over element length plus 1, sample length, element length. It's extremely simple in this case because I'm using an extremely idealized material law. If you work it out, you get a regularization curve. You get a failure strain in function of the element size. And that regularization curve for this very simple example is a logarithm of a hyperbolic function of the mesh length. For real material laws, it will be something else, and you cannot derive it as in a way as simple as I just did. In fact, you'll have to determine it by simulation, step by step. But the principle is not different. So Marian was so kind to do some simulations to make that clear. And you see the principle here when we model a real life tensile test with a very coarse mesh and a somewhat finer mesh of say 0.5 millimeter. And you apply a certain displacement to both models, you see that the strain values that we get in the fine mesh are much, much higher due to the localization. If there would be no necking, it would be the same. But since there is necking, we get strain values that are very different. And for a given strain to failure, the finer mesh will, of course, fail first. Now, this is the reason that we absolutely need regularization when we do applications, because your mesh in a real-life model is never homogeneous. You always have a mixture of small elements and larger elements. And if you have no regularization, the failure pattern will actually be dominated by the local element size rather than by the physics. So we did an example on Uzi board 1500. We modeled a typical tensile test. Marian generated a biquad failure criterion and determined a regularization curve, which is basically a scale factor applied to the failure curve, where the failure curve is a function of triaxiality. And you see that that scale factor is 1 for a mesh length of 1, which happened to be the mesh size for which the material model was validated. And then as the mesh size becomes larger, we have to bring that scale factor down. And as you can see, we don't have to bring it down by just a little bit. It goes down by about 30% in this moderately severe example. We can take the time to look at the video. It's run with mesh sizes of 1, 2, 5, and 10 millimeter. There is regularization on the right-hand side. You will see them all fail at the same time. There is no regularization on the left-hand side. You will see them fail sequentially from right to left. Coarser the mesh, the later it fails. And we have some snapshots to confirm that. You see the initial failure here. With a 1 millimeter mesh, they are simultaneous. It doesn't matter whether you have regularization or not. With regularization, all meshes go almost simultaneously without regularization. After the 1 millimeter comes the 2. Quite a bit later comes the 5 millimeter mesh, and finally the 10. If you put that in a graph in terms of force displacement, you see what happens here. The red curves are without regularization, so the coarse meshes fail later. The blue curves are with regularization, and we manage to make them fail all at the same value of the displacement. Now that graph shows you the power and the limitation of regularization. What we regularize is the displacement at failure. You could choose to regularize many other quantities. You could focus on energy, you could focus on whatever. Obviously, the best would be if you could regularize the entire load path. There are methodologies that do that, but they obviously require a little bit more effort from the user than what I just showed. In the end, it's all a question of what is the payoff that you're going to get for your efforts when you do a real-life application. And that has to be judged on a case-by-case basis. So regularization works. At least in uniaxial tension, it works. Well, it works because in uniaxial tension, there is no doubt that we have necking, that we have localization. That will be the case for the vast majority of metals, with the exception maybe of a few castings. But it's not always the case. Under pure shear conditions, we will not generate any change in volume. We will not generate any change in cross-section. And if the material has no softening, and metals under quasi-static isothermal conditions do not have any softening, then there will be no localization. And to regularize your failure model will be extremely misleading. In other words, regularization is stress state for triaxiality dependent. And there is a dramatic example of that in the next slide. You see a part here of a component in a full car simulation, and on the top you see a deformed shape, and the red dots that you see in the middle and in the right-hand side plot are eroded elements. So you see a buckling mode of that extrusion profile, and you see a moderate amount of failure. In that simulation, we had no regularization, and it behaved perfectly. With regularization, you get the nonsense that you see on the lower row. Massive amounts of erosion, way too much failure, and basically a shear off of the top plate from the rest of the profile. It opens like a can of sardines. That's not what happened. That's not what happened at all. And the reason for that is that we had a failure model there calibrated for a 1 millimeter mesh. In the application, we had a 4 millimeter mesh. It was regularized based on uniaxial tension. You apply that regularization to a state of shear, and you fail way too early. You get a time bomb. So we're going to have to make our regularization stress state dependent. But for that, I'm going to have to know, when does localization start under biaxial loads, under shear loads? When does regularization start for a given value of the triaxiality? Well, if we limit ourselves to plane states of stress, that's a question that's been answered by this guy. Herbert Walker Swift, and he wrote a paper in 1952, so I was not born yet. So I certainly didn't read that one until much, much later. But at least I didn't reinvent the wheel. Whatever was there, I used. I'm going to briefly walk you through the Swift criterion and what we can do with it. It's really quite simple. First, you have to prepare some notations. He was looking at plane stress conditions. And in fact, he was looking at biaxial tension. So two principal stresses that are both in plane and both positive. And then you can write a stress tensor as the first principal stress multiplied by a matrix where we have a 1 in the 1,1 component, a value A in the 2,2 component, and 0 for all the others. That factor A is the ratio of the second principal stress to the first. And if you work it out, you can calculate the triaxiality, which is pressure over von Mises stress, and you see that that is a function of A. So this A contains the same information as the stress triaxiality. You can identify it with a state of stress. To get to the simplest example, if A is 0, you have uniaxial tension. If A is -1, you have pure shear. And if A is +1, you have equibiaxial tension. So this is then what he considered. You take a sample, you load it in tension in two directions. In the first direction, you have a force F1. In the second direction, you have a force F2. You have strain rates epsilon.1 in the first direction, epsilon.2 in the second direction. Swift made a very simple assumption. I think nobody knows where it comes from. I don't think he knew. He just figured out that it somehow worked. He made the assumption that in the two directions, we simultaneously reach a force maximum. So we reach a state where dF1 and dF2 are simultaneously 0, which is a straightforward generalization of the considered criterion. The only thing I can say is don't think about it too much, because the only thing you'll get from that is a headache. Believe me, I tried it. Well, you work that out. You assume that your material response is isochoric, and your conditions translate in two differential equations for the stress rate in function of the stress and the strain rate in the corresponding direction. You then neglect the elastic deformations. You identify the total strain rate with plastic strain rate, and you replace the plastic strain rate by the flow rule, so by the equivalent plastic strain rate, and the derivative of the yield stress or the von Mises stress, you can use them interchangeably with respect to the corresponding principal stress component. The last thing you have to add are the classical plastic loading conditions, where we say that we're in a condition where the yield stress is equal to the von Mises stress. And you have to add the same thing with a dot, showing that we're actually evolving in a way that we stay on the yield surface. It then takes about 1 page of algebra, it's not very big, to derive the condition that expresses that simultaneous equilibrium of the two forces. And what you end up with is that the tangent modulus, the derivative of the yield stress with respect to the equivalent plastic strain, the tangent to the yield curve, has to become equal to the yield stress multiplied by a function of the state of stress, and to be more precise, by a function of that factor, A. And then we're going to have to solve that equation for every value of A and find for which value of the equivalent plastic strain it is fulfilled. Now you can immediately see that it's consistent. In the uniaxial case, when A is equal to 0, that whole multiplicative factor becomes unity, and you end up with the consider criterion. So you fall back on something you know, you fall back on your feet. Well, once you have that equation, you can use it. So given you have a yield curve for a certain material, that would be the blue curve. You take the derivative of it, so you derive that yield curve with respect to the equivalent plastic strain. That would give you the green curve. Wherever these two curves intersect, that is the strain at necking. That is the start of localization for a triaxiality of 1/3. If you now want to know the start of localization for any other state of stress, you compute the value of A. That gives you a multiplication factor for the red curve. You move your red curve up or down by that multiplication factor, and you look for the intersection point with the green curve, which you don't touch. And that gives you the value of equivalent plastic strain, where localization starts for that particular state of stress. So you can very easily implement that with Excel, which is, I think, what you did, Marin? Yeah. Here you see what you can get with that. In the left upper corner, you see a yield curve. And right next to it, you see a plastic strain at start of instability in function of triaxiality, where my triaxiality here is positive in compression. So the negative values correspond to tensile states of stress. I did that on purpose. No, I didn't. One little remark, you see the red line go to 1 for a triaxiality of 0. That's a quirk of the program. In fact, it never intersects with the vertical axis at triaxiality 0. It would intersect at infinity. In other words, this criterion clearly confirms that there is no localization under pure shear conditions, that your fracture under pure shear conditions is brittle. And you don't need regularization there. You can transform that criterion in function of other quantities. Maybe the most familiar one is here, where we plot the major plastic strain in function of the minor, and then it looks like an FLD. It looks like a forming limit diagram, but it's not, of course. A forming limit diagram gives you the start, the onset of localized necking. And what we have here is the onset of diffuse necking. So you're much lower. About a factor of 2. I have a bunch of remarks. I'm not sure I want to go through all of them, but maybe of this entire page, the only one important is the one in red. It's that this method indeed predicts no instability under quasi-static shear loads. That doesn't mean, of course, that it never happens. We have no temperature effect here. If we would include thermal softening, you would very, very naturally get an onset of localization under pure shear. And that would be an adiabatic shear band. But we didn't include that here. Second set of remarks, you can generalize this as much as you want. We have written the equations for a 2D Swift, taking the elastic strains into account. We've done a 3D Swift assuming rigid plastic material and a 3D Swift taking elastic strains into account. And you can even do it for compressible materials. So you can do it for plasticity theories that allow permanent volumetric straining. Materials that have a plastic Poisson coefficient that is not equal to 0.5. And we're going to implement all that, right, Marion? Finally, why Swift? There are many, many other 2D localization criteria. If you look at the literature, you have the global bifurcation criterion, you have the limit point bifurcation criterion, there's the maximum force criterion, there is the Belichko and Zhu criterion. Why did we pick Swift? Well, number one, it's very simple. Number two, as long as the material is not rate dependent, and these things become very, very complicated once you consider rate dependency. But as long as your material is not rate dependent, we could actually prove that it gives the same results as the limit point bifurcation criterion, which is much more complex and has a much more solid mathematical foundation. But the main reason is that we tested it. You can't really test it experimentally, but you can test it numerically. Numerically, you can build test cases where you take a plate of finite elements and you subject it to loads with any triaxiality. And you can check when localization starts. Well, we've done that for, I think, 100 data points. And the start of localization was always spot on the Swift prediction. So it works out amazingly good. And if you want to know more of that, we've published 2 papers on that, which were presented in Bamberg in 2022. They're on the internet, so you can easily download them. One pitfall, you need smooth yield curves. And you need very smooth yield curves. You don't always see that you have a problem. You see 2 yield curves for an HSLA for a high-strength low alloy steel here. One is, the red one is the original one, the green one is the smoothed one. They look the same on this picture, but they're not. If you actually look at the derivative, you see that in the right upper corner, and you see a zoom in the lower right corner. You see that the original tangent was not even monotonically decreasing. We had some oscillations here and a slight increase. And with the smoothed version of the yield curve, that pathological behavior disappeared. Well, the result of that was that with the initial non-smoothed curve, we got this instability curve with a dip in it. If you get that, it's obviously suspect, but you're not sure if it's wrong. But you can very easily verify, because you know for a triaxiality of 1/3, you know the necking strain. So you can check here if you have the right value, and if you don't, there's something wrong. With the smoothed curve, we got the green curve, which not only looks better, but has the right value for uniaxial tension. So it is somewhat sensitive to the smoothness of the yield curve. It's actually very sensitive to the smoothness of the yield curve. And you have to make sure that you don't generate nonsense there. Well, I finally come to what we did. So we somehow have to come up with a regularization that is triaxiality dependent. We can determine a regularization curve for uniaxial tension. We're not going to escape that. We will always have to do that. And we know that under pure shear, we don't have to regularize at all. But what do we do for other triaxialities? Well, the idea is to make the remedy proportional to the disease. I mean, that's what medical doctors do, right? You have a cold, they give you a little bit of penicillin. You have the flu, they give you a little bit. And we're at the same level here. The mesh dependency will depend on the localization. It will depend on the plastic deformation that we see beyond the onset of localization. So we're going to take our failure criterion, which gives us a plastic strain at failure. And we're going to take the instability criterion, which gives us the onset of localization. And when we subtract one from the other, we have, if you want, the ductile plastic deformation, the part of the plastic deformation that is problematic in the sense that it causes mesh dependency. So that's a very simple process. In step one, we take our yield curve and we take the derivative. We have to smooth that out a little bit. In step two, we compute with the process that I previously described, the instability curve, which is the green one. We're going to have to smooth that one out a little bit too. And we combine that with the failure criterion, which can be anything. It's the red curve here. And in this case, that was a modified Morcoulomb, but it could be anything. It could be something that you tabulated from experiments, wherever you get your failure criterion from. And you see that the two curves cross over for some positive triaxiality. Now my triaxialities are positive in tension the way they should be. Well, as long as the instability curve is above the failure curve, we don't have to regularize, so we're fine. When the failure curve is above the instability curve, we have to regularize. So we're gonna subtract one from the other. And we've done that here. Obviously, the value of that subtraction is 0 in the intersection point. And when we get a negative, we set it to 0. Sometimes we have two intersection points. There could be a second intersection point here in the neighborhood of equibiaxial tension. That did not happen for this particular material. So the blue curve is a normalized measure for the ductile plastic deformation, the amount of plastic deformation that will give rise to mesh dependency. And we've normalized it here for a triaxiality of 1/3. We've normalized it to a value of 1. Well, with that, we're now going to generate a regularization function for every triaxiality. And we do that by linear interpolation. So for every triaxiality, we compute failure strain minus swift strain, and we divide that by failure strain minus swift strain for a triaxiality of 1/3. We cut the value at 0. That gives us a factor alpha. And then we interpolate between the regularization function at a triaxiality of 1/3, which is the blue curve, and a unit curve, which is no regularization at all, which is what we do to the left of the intersection point, and that is just a horizontal unit function. Doing that, we get a regularization function for every triaxiality. And with that, we can now visualize a mesh-dependent failure criterion. The black line is the failure criterion for our initial mesh size, say 1 millimeter, the one for which we validated our material. And then for increasingly large meshes, we reduce by a certain amount for a triaxiality of 1/3 in uniaxial tension. At the intersection point between the instability curve and the failure curve, we stop applying a factor, and our failure criterion is mesh independent. And in between, we have a linear interpolation. So we've done some single element test verification. That's actually very elementary, and it just shows that the implementation works. I'm not going to go into that. I mean, we've done our homework. I just want to say a few words about the next step. Our next step is definitely going to be a 3D version. With a 3D version, we're going to have a 3D Swift. That means there's going to be 3 simultaneous force equilibria, 3 simultaneous force maxima, basically in the 3 orthogonal directions, 1, 2, and 3. The equations are there, we just have to implement them. That means that the Swift curve will become a Swift surface defined by a number of curves at different values of the Lodi parameter. So we just have to generate one for every Lodi parameter at which we have a failure curve, and then we can combine them one by one in exactly the same way as you just saw. So that's going to be, although the equations are somewhat more complicated, that will be a pretty straightforward process. So these are the conclusions. Regularization of failure criteria is a necessary evil. If you have a ductile material, you have to do it. I've had many customers that said it should be, I hate it so much that it should be illegal. Well, my answer to that is I hate paying taxes, but I pay them. If you live in the United States, you pay. Yeah. So it's not an option. It's not disputable. The amount of regularization that you need depends highly on the triaxiality of the load path, and in the case of brittle failure, for instance, pure shear under quasi-static conditions, it becomes 0. We've implemented something very pragmatic that is triaxiality dependent. For the moment, it's limited to plane stress. The beauty is it requires no user intervention. You don't have to do anything. All you need to do is get a regularization curve for uniaxial tension. So there is no additional work to what you already do. Now, is it perfect? Of course not. Nothing is perfect. The Swift criterion is actually path independent. The failure criterion is not. We know that failure is quite path dependent. So we're combining something that is path independent with something that is path dependent. As long as you do proportional loading, it works, of course. But under highly non-proportional loading, well, application will show. Experience will show. That's it. I've made a habit of coming to the OpenRadioss users conference every year. And I made a habit of dedicating my last slide to the city in which the conference takes place. The first time I came to Gothenburg was 1985. And it is, of course, the city of Starköl, Absinthe, and Surströmming. All 3 of which I have enjoyed to a high degree. many, many times, so I have tremendously good memories of this city. But it is also, to a high degree, the city where my career as a consultant started. In fact, the second contract I ever had when I worked for myself was with Volvo. And my client was the gentleman that you see on the picture in the left lower corner, Jan-Olaf Christiansson, with whom I worked together for many, many years, at least a decade. And he was more than a client, he was a mentor. So with that, this is a tribute to Jan Olaf and all the work we did together and the good memories of Gothenburg. Thank you.